Atomic structure, stable and unstable nuclei, particles in radiation unit 1. Nuclei are positively charged because there are protons only with a charge in the nucleus. The protons and neutrons are the only two particles in the nucleus. Protons are positive and the neutrons have no charge. Keeping it stable requires a very strong force. Unstable nuclei will decay to be stable because positive and positive will repel each other. Hence, they can fly apart, but they did not fly apart. So what's holding them together? What holds the nucleon together? Protons and neutrons are called nucleon. 4 fundamental forces are holding the nucleon together. But first, let's talk about the diameter of a nucleus. The diameter of a nucleus is between 1 to 15 femtometers. A femtometer, a femto is 10 to the power minus 15. 1 femtometer is 1 times 10 to the power minus 15 meters. 15 femtometers is 15 times 10 power minus 15 meters. So the 4 fundamental forces that are holding nucleons together in the nucleus, one of them is gravitational force. Gravitational force, GF, is an attractive force. The property of bodies with mass. Nucleons attracted each other due to their masses. It is long-range force. It's also very weak. Gravitational force is mediated by graviton. It's an infinite force in the terms of range. Comparing the Earth to a human, the mass of Earth is much bigger than human, so therefore humans are attracted to Earth far more than Earth is attracted to human. And so that's why we fall to Earth. In the nucleus, the mass of a proton is 1.673 times 10 to the power minus 27 kilogram. The mass of a neutron is 1.675 times 10 to the power minus 27 kilogram. So the masses are relatively similar. So therefore, the gravitational force is very weak in the nucleus, but yet it's present. The reason for that is that you would expect the protons to pull each other apart. So there must be another force that is helping the protons to stay intact in the nucleus. Electromagnetic force. Electromagnetic force is the other force, number 2. EMF is a repulsive force in the nucleus. But electromagnetic force can be attractive force and repulsive force. Protons will attract an electron. Protons will repel a proton, so that's attractive and that's repulsive. Electron will repel another electron. Again, that's repulsive. So in this case, in the nucleus, it's a repulsive force. The electromagnetic force are mediated by virtual photons. So photons is the energy due to light. It's an infinite range electromagnetic forces. So the next one is a strong nuclear force. The strong nuclear force holds the nucleons together. It works equally between all nucleons. So it has the same effect with neutrons and protons as it is with neutrons and neutrons, as it is with protons and protons. So the effect is the same thing. So here's a diagram to showing the short range effect of a strong nuclear force. There are 2 parts in this diagram. The negative value, the force is in the y-axis, and in the x-axis is the distance between the nucleons. So for instance, protons and protons, the distance apart, that distance is more stable at 0.5 femtometer. So at 0.5 femtometer, or between 0.4 and 0.5 femtometer, this distance is where you have a stable distance between the two particles, and the same distance between protons and neutrons, and the same distance between neutrons and protons. And that distance is at 0.5, where the resultant force is 0. The negative bit here is the attractive force. So the attractive force is increasing as we go along the distance. So if we start to separate these two distances, so this distance is 0.5 femtometers. And if we start to separate them, make it longer, then the attraction force will kick in and try to bring them back together. And if we bring them beyond that distance, which is 0.5 femtometers, say 0.1 femtometers, the repulsion force will kicks in, trying to push them apart. So the repulsion here will kicks in, trying to push them apart. The electromagnetic force is completely repulsive here. So that's the electromagnetic force there. And this is the attractive force here. And the point here, the attraction, so if you start to separate them, the attraction will start to increase until it gets to about 3 femtometers apart. And then beyond that, the attraction would start to decrease. So that means it's not, it stops there, and then it doesn't bring them back apart and bring them back together again. And as you can see, at 3 femtometers, attraction starts to decrease to 0. It approaches 0 here. So this is a turning point where it started. It was increasing all the way there, and when it gets to that point, and it starts to decrease back to the rate of increase start to decrease, and then start to decrease back to 0. The fourth one is the weak force. This is called the weak force. It's a short-range force, and it's responsible for beta minus decay in the nucleus. It's mediated by W and Z bosons. W minus mediate beta minus decay, and W plus mediate beta plus decay. So the strength of these forces, all 4 of them, relative to gravitational force, if gravitational force is 1, the weak force is 10 to power 25 times bigger than gravitational force in the nucleus. The electromagnetic force is 10 to power 36 times bigger than the gravitational force. And the strong nuclear force is 10 to power 38 times bigger than the gravitational force. Those are the 4 fundamental forces that is holding the nucleons together in the nucleus.